It's me again. In the last video lesson, we learned about valence electrons. We learned about how to use the periodic table to figure out how many valence electrons are in the elements in any particular column. This video lesson, we're going to talk about something called the Octet Rule. The Octet Rule is important in chemical bonding. And then I'm going to introduce to you the concept of ionic bonding and also explain to you why ionic bonds happen. Finally, I'm going to show you how you can use your periodic table to predict the charge of any particular element based on its position on the periodic table. It has to do with the valence electrons. So buckle up, get your notebook ready, here we go. The first thing we're going to talk about is the Octet Rule. The Octet Rule says that elements are happy when they have 8 valence electrons in their outermost energy level. Did you ever notice that the last column on the periodic table has 8 valence electrons? We covered that in the last video lesson. And if everything here has 8 valence electrons, then it, by definition, are the happiest elements on the periodic table. Now, every other element besides the noble gases are either going to lose electrons, gain electrons, or share electrons in order to achieve 8 valence electrons in their outermost energy level. And that is the whole reason why chemical bonds occur. That's the whole reason why two elements find each other and stick together, is so that they can create 8 electrons in their outermost energy level. Now, I went ahead and jotted in the number of valence electrons in each column of the periodic table. This is a review from last video lesson. This first column has 1 valence electron. These elements all have 2. Boron, aluminum, gallium have 3. Carbon and friends 4. Nitrogen and friends 5, 6, 7, and 8. We just talked about how these noble gases are the only group on the periodic table with 8 valence electrons. Notice how groups 1 and 2 and 3 are all consisting of metals, with the exception of hydrogen, which is a nonmetal, but it acts like a metal, and so that's why it's listed over here in group 1 of the periodic table. Do you see how they have 1, 2, or 3 valence electrons? Well, that's important because these metals want 8. Now, they have 2 options. They can either try to fill up their outermost energy level to achieve 8 valence electrons, or they have another option. They could get rid of electrons to open up an inside energy level. Let's take, for example, sodium. Sodium has 11 total electrons. The first 2 electrons are in the first ring, the next 8 electrons are in the second ring, and it has 1 lonely electron here in its third ring. As I mentioned, sodium, with its 1 lonely electron, could add 7 more to this third ring, but that seems like a lot of work, doesn't it? Adding 7 electrons to the outside ring. Atoms, like humans, are pretty lazy. They just want to do the minimum amount of work and try and get away with it. And so sodium's like, adding 7 electrons? That seems kind of like a lot of work. So, you know what I'm going to do instead? You know what I'm going to do? Hey, look at this. Do you see how my second ring is already filled with 8 valence electrons? What if I just get rid of this outside ring? And now sodium has a full outside valence electron energy level. But it lost an electron in order to do that. But it kept the same number of protons in the middle of the atom. It still has 11 protons, but now it has 10 electrons. And since it has 1 more proton than electron, it is now a +1 charge ion. Again, why did it get rid of its electron? Because it really wants 8 valence electrons, not just that 1 loose one. And it will do anything it can to shed that outside electron. And by losing that electron, it now has 1 less electron than it does protons. So the charge of the ion now is a +1 charge ion. In fact, all metals behave similarly to sodium. All metals will want to get rid of their valence electrons in order to open up an inside ring that is already full. It is the easiest to do. And so all these elements in the second column of the periodic table will all try and get rid of their 2 valence electrons in order to open up the inside shell. It loses 2 electrons and becomes a +2 charge ion. Boron, aluminum, and gallium, these elements will all try and lose 3 valence electrons in order to get rid of their outermost electrons. And when they do that, just like sodium, they open up a full inside ring. And so metals lose electrons and become positively charged always. Now you might be asking yourself, sodium gave away its electron, where did it go? Well, fortunately, there are some elements on the periodic table, unlike metals that want to get rid of their electrons. There are things like nonmetals that are just thirsty for electrons. They want electrons whenever they can find them, and they will pick up electrons from metals that want to get rid of them because they're a perfect match. It's like peanut butter and jelly, like spaghetti and meatballs. They just go together perfectly. So just like metals, nonmetals also want 8 valence electrons. And they also have these same two options to choose from. They could fill up their ring to make 8, or they could get rid of electrons to open up a full level. Now I will spoil this for you already. Since metals do this, nonmetals will not do that. In fact, nonmetals will choose to fill up their outside ring to make 8 valence electrons. Notice the majority of the nonmetals are located in the columns where they have 5, 6, or 7 valence electrons. Now, noble gases have 8, so they will not take any electrons or they will not give any of their electrons away. They are completely happy. So we're talking about the elements in the nitrogen, oxygen, and fluorine columns of the periodic table. Now, these elements will fill up their rings to make 8 valence electrons. Let's take, for example, fluorine over here. Fluorine has 9 total valence electrons. Now, the first 2 electrons go on the first ring, and the next 7 go on this second ring. Notice there is one spot open for an electron to go into, and that's where sodium comes in. Sodium was looking to get rid of its electron, and fluorine is looking to take on an electron. And so fluorine will take that extra electron that sodium is ready to give. I'll highlight it here in red. This is the extra electron from sodium. Now that sodium has gotten rid of its electron, it is a plus charge. Now fluorine, since it has 9 protons, and now it has 10 electrons, it is now a -1 charge ion. And that is a perfect combination because sodium being a +1 charge ion and fluorine being a -1 charge ion, now they can form an ionic bond. You originally had 2 neutral atoms, sodium with 11 electrons and fluorine with 9 electrons. But those two did not necessarily attract one another because they're both neutral. But when sodium gets rid of one of its electrons to fluorine, sodium becomes positively charged and fluorine becomes negatively charged. And when sodium and fluorine are close to one another and they're opposite charges, well, what do opposite charged things do? They attract. And that attraction that they feel between their opposite charge is what we call an ionic bond. So in summary, metals are likely to get rid of their electrons to fill up their energy levels, and that results in positively charged ions, whereas nonmetals are likely to gain electrons to fill up their outside energy levels, and that results in negative ions. And when positive ions and negative ions come in contact with one another, they attract and form an ionic bond. On this page, we're going to talk about how you can use the periodic table to predict the charge of the ion of any element based on its position on the periodic table. Now again, over the top, I've jotted down the number of valence electrons that each particular element in that column will have. And on the last slide, we talked about how elements in the first column are likely to lose that electron in order to become +1 charge. Same with the second column, those are likely to lose their 2 electrons and become a +2 charge. And so we're going to start to generate a pattern on the periodic table that corresponds to the position and the charge of those ions. Now in the third column, these elements will all lose 3, and when they do, they will become +3 charge ions. Now this column right here is kind of the halfway point of the periodic table. It doesn't look like the halfway point, but it is the halfway point. Because if you exclude the transition metals, then there really is only 8 columns, and this is the halfway. Now these elements could either gain or lose 4 electrons. It's all about whether or not it's easier to gain 4 to look like 8 or to lose 4 to open up an inside shell. And so these will neither gain or lose. They are much more likely to share their electrons than gain or lose electrons. But let's just say, for the sake of conversation, they may gain 4 electrons to become -4 charge or lose electrons to become +4. Now on this side of the column, we're thinking about nitrogen and phosphorus. These elements are now more likely to gain electrons to fill up their outermost energy level. So by gaining an electron, you become a negative charge. So they gain 1, 2, 3 to look like a noble gas or have 8 valence electrons. So these elements will all be negative 3 charge. Oxygen and friends are 2 electrons away from having a full shell, so they will gain 2. And every time you gain an electron, you become negatively charged. So -1, -2. These are all in the -2 charge ions. The halogens in group 17 are all 1 electron short of a full shell. That makes them very reactive, and they will gain an electron whenever they can. When they gain 1 electron, they become -1 charge. And of course, noble gases with 8 valence electrons do not gain or lose any, and they will have 0 charge. Now I hope you also jotted these charges down over the top of each column on your personal periodic table so that it can help you with this next activity. So basically what I'm going to do is just say, what is the charge of the following elements when they lose or gain their valence electrons? And so the examples I'm going to give you are sodium, fluorine, argon, silicon, sulfur, and calcium. Now, of course, we did these first 2 on the last page, so these should be easy. Sodium is going to lose 1 electron and become a +1 charge. And that's supported by the fact that it's in the first column and I labeled it +1 charge over the top. Fluorine is in the 17th column. These all have 7 valence electrons, and it will gain 1. In other words, it'll be a -1 charge ion. Now what about argon? Argon is in the noble gases, and noble gases have 0. Why don't you pause the video now, see if you can figure out these last 3, and then go ahead and hit play, and I'll tell you the answers. So silicon is in that column that we talked about underneath carbon and germanium, where they have 4 valence electrons. So they could gain 4 or lose 4. And so in this spot, I'm going to put +4 or -4, because it could be either or. Now for sulfur, once you find it, it's number 16. It's in the column with oxygen. And over the top, -2 charge, because they have 6 valence electrons and they gain 2 to become -2 charge. And finally, calcium, which you'll find over here as number 20, has 2 valence electrons, and because it has 2 valence electrons, it will lose them to become a +2 charge. It's important to remember that when an element loses electrons that subtract a negative, it actually becomes positively charged. And when it gains a negative, or in other words, adds a negative, then it becomes more negative. Metals are positive. Nonmetals make negative ions. Well, that takes care of this video lesson on ionic bonding and predicting ionic charge. Thanks for watching.